Good evening. This is Boaz and we continue with our program of MET 415. Today's topic is going to be vector algebra. What I'd like to do is show you first an example of an application of vector algebra in robotics, and then discuss some useful operations such as the cross product and the dot product. What we have here is an example of our educational scoreboard, and it has an inertial frame fixed to the shop floor. It has a base over here, and over here up at the gripper it has a moving coordinate system, which we call it coordinate system 4, x4, y4, z4. Now in this example we have an acceleration vector A, and it is calculated in the inertial coordinate system. And the inertial force is equal to the acceleration times the mass, which is a scalar with a negative sign. In other words, if this is the inertial force, it means that the acceleration is exactly in the opposite direction. So if the acceleration in this direction, the inertial force will be in this direction with a minus sign. We also have here a position vector r going all the way from the joint where the motor is acting to the point of action of the force. The cross product of the position vector to the point of application of the force and the force itself is the torque. And the torque actually operates at the joint, and it's useful for us in order to find the motor torque, and the motor torque is along this axis. In other words, it's the resolution of the total torque along this axis. The way to find the resolution of this torque along this axis is to do the dot product of the total torque times a dot product with a unit vector along the y-axis. And that gives us a vector, which is the torque motor, in the direction of vector, unit vector y4. These are an example of a typical problem that we encountered in robotics. Now, to learn a little bit more about the cross product, let's take a look at the coordinate system, general one, and two vectors, r1 and r2, which are separated by an angle alpha. Now the question is, what is the cross product? The cross product is a vector which is perpendicular to both of them. It has a magnitude which is equal to the magnitude of r1 times magnitude of r2 times the sine of the angle in between. Now the magnitude of r1 is given as the square root of the sum of the squares of each one of the components. These are the components, this is the sum of squares, and this is the square root, giving us the magnitude of r1. Similarly, we find the magnitude of r2 from its component. Now, this is the cross product magnitude. The direction we find based on the right-hand rule. When we rotate r1 towards r2 at an angle theta, then a direction of the cross product will be the direction which a right-hand screw will advance. So if r1 is rotated into r2, this will be the direction of the advancement of the screw. So that is the direction of the product. We can also find the components of the cross product by taking the determinant in a certain way. We put the unit vectors up on the first row of the determinant. We put the components of the first vector on the second row, and we put the components of the second vector on the third row, and then we do the determinant by taking, first of all, these two components, which is r1y times r2z. We have them here, minus these two components, times x, which is R1z times R2y. Here they are. Then what we do is we take the second component of the cross product, is the one related to the y, which is R1x R2y. And no, I'm sorry, this is for this one it will be R1z times R2x. Here it is. R1z times R2x actually connect the y, and then in this direction, parallel to this line, it will be R1x times R2z. Here it is. And the last component will be for the z direction, which will be R1x R2y. Here they are, minus R1y R2x. So this basically completes the definition of the cross product. Let's take a look now at the dot product. We have the same two vectors. If you want to take the dot product between them, we designate it as such, and it is a scalar. Dot product of two vectors is a scalar. We call it R3. The scalar magnitude is equal to the magnitude of the products of the two vectors times the cosine between the two vectors, as we see over here. And to find out the magnitude, we could also do the operation of taking the transpose of one vector and multiplying it times the other vector, and the result will be the first component times the first component of the second one, the second component of the first one times the second component of the second one, and the third of the first times the third of the second. And here's the result of the dot product. These are pretty much the two basic operations which I wanted to discuss with you. And our next episode will see how easy it is to use them using MathCAD. Thank you.